Have you ever wondered why, even with all our scientific breakthroughs, a complete cure for AIDS remains elusive? It's such a complex challenge.
It really is.
While modern anti-HIV drugs, dramatically slow the virus, HIV is a master of disguise. It constantly mutates, subtly changing its shape.
Making it resistant to our carefully designed medications.
Exactly. But here's where chemistry steps in with a truly innovative approach. Scientists have developed a new class of promising anti-HIV drugs and their secret weapon.
Flexibility.
Yes. They're designed to be incredibly flexible. This molecular flexibility allows them to adapt and continue binding to the virus, even as the virus tries to change its geometry.
Which is a crucial step in the ongoing fight against drug resistance.
Absolutely.
And that idea of molecular flexibility of molecules literally bending and twisting, well, that brings us right to the core of today's deep dive, conformational analysis.
Okay.
At its heart, it's basically the study of the dynamic, three-dimensional shapes that molecules can adopt. Think of it as understanding a molecule's internal sort of dance moves.
Dance moves, I like that.
Yeah, and to truly grasp this flexibility, we really need to start with the simplest building blocks in organic chemistry, alkanes and cycloalkanes.
Right, the basics.
These are molecules made only of carbon and hydrogen, without any rigid double or triple bonds. Our mission today is to explore exactly how these fundamental molecules change their 3D shape, primarily through the rotation of their carbon-carbon single bonds.
And that rotation has big consequences.
Oh, absolutely. It's more impactful than you might think, influencing everything from gasoline to life-saving drugs.
So we're going on a bit of a journey then. We'll start by understanding the system for naming these compounds. Because if you can name them, you can start to understand their structure.
That's the foundation.
Then we'll dive into how they actually bend and twist, exploring the sort of hidden energetic costs of these movements.
Right, the conformations.
And finally, we'll connect this understanding of molecular shape to powerful real-world applications, from designing those flexible drugs we just mentioned all the way to, well, diamonds.
Exactly, it all connects.
Okay, let's get started.
So let's lay the groundwork with hydrocarbons, compounds made exclusively of carbon and hydrogen. Take ethane, for example, C2H6.
Simple enough.
Unlike molecules with rigid double or triple bonds, what chemists call pi bonds, ethane contains only single carbon-carbon bonds. That's a key distinction.
Okay.
We call these saturated hydrocarbons, or alkenes, and their names almost always end with that familiar ane suffix, like propane, butane, pentane.
Right, you hear those all the time. It's wild to think that in the early days, organic compounds were often named, well, pretty whimsically.
Oh, yeah.
We had formic acid from ants, urea from urine, even morphine, named after Morpheus, the Greek god of dreams.
Wow.
And many of these common names are still used today, which I guess speaks to their initial convenience.
But as the number of known organic compounds just exploded, a systematic approach became absolutely essential. Scientists needed a common language.
Makes sense. Communication is key.
Precisely. This led to the Geneva Rules back in 1892, eventually evolving into the International Union of Pure and Applied Chemistry, or IUPAC.
IUPAC, heard of them?
These IUPAC rules provide a consistent, universal way to name compounds, no matter where you are in the world.
So how do we actually bring order to this molecular chaos? How does IUPAC work?
Well, the systematic approach starts with identifying the longest continuous chain of carbon atoms. We call this the parent chain.
The main backbone.
Exactly. And knowing your basic parent names, like methane for 1 carbon, ethane for 2, all the way up to decane for 10, that's your entry point. You really need to memorize those first 10.
Okay, first 10. Got it.
And here's a neat little tiebreaker rule.
Yeah.
If you find 2 chains of equal length, the correct parent chain is the one that has the greater number of branches attached to it.
More branches wins.
Right. Sure is a unique name. We also use the cyclo prefix for alkenes containing a ring structure, like cyclopropane or cyclohexane.
Okay, so you've got your parent chain. What's next?
Then it's all about naming the branches, or substituents, that hang off it.
The things attached.
Yeah. We do this by taking the parent name and adding ul, so a 1 carbon branch is methyl, a 2 carbon branch is ethyl, propyl, butyl, and so on.
Methyl, ethyl, propyl.
Okay. It's an elegant way to precisely describe what's hanging off that main chain. Sometimes a ring itself can be a substituent, or it might be the parent, depending on its relative size to the chain. The power of this system is that it gives every single organic molecule a unique, universally understood address.
This might seem purely academic, but Understanding these names, it lets us unlock the chemistry of nature itself. Take pheromones, for instance.
Oh, good example.
These are chemical messengers animals use. The moth affects pheromone, 2-methylheptadicane. It's a precisely named alkane. Its exact structure, dictated by these rules, is critical for its function.
It's the language the natural world speaks, and nomenclature helps us decode it.
Right. And sometimes those branches themselves have branches.
Ugh, complex substituents, yes. The system still works, though. You name them as a kind of mini-parent with their own numbering, starting from where they attach to the main chain.
And put their name in parentheses. Okay.
Exactly.
The good news is IUPAC also approves of many common names for these frequently encountered complex substituents, things like isopropyl, sec-butyl, or tert-butyl.
Yes, those are very common. You'll see them all the time. They act as convenient shortcuts.
And these concepts aren't just abstract, right? You mentioned bile acids.
Right. Bile acids, crucial for digestion. They have very complex side chains. Understanding how to systematically name even their hydrocarbon cores is fundamental to understanding their biological roles.
So finally, we bring it all together by numbering the parent chain to give locants. Numbers, right? Identifying each substituent's position.
Correct. And the core rule is give the first substituent the lowest possible number.
Lowest number wins. What if there's a tie?
Good question. If there's a tie, you look for the lowest second locant. And if it's still tied,
Alphabetical order.
you got it. Alphabetize the substituents to decide the numbering order.
Okay. And what about multiple identical groups, like two methyls?
Then you use prefixes like di, tri, tetra,
Yes.
so dimethyl, trimethyl. Just remember one tricky bit. These prefixes are generally ignored when you alphabetize the substituents.
Ah, so dimethyl is alphabetized under M, not did.
Exactly. Same for second, third, but iso is included in alphabetization.
Okay, so to quickly recap the naming process. First, find that longest carbon backbone, the parent chain.
Right.
Second, name all the branches, the substituents.
Yeah.
Third, number the chain to give the branches the lowest possible numbers following those tiebreaker rules.
Correct.
And fourth, assemble it all alphabetically, putting it together.
That's the system. It's how we categorize and understand everything from simple molecules to complex ones, like the components found in everyday fuels like kerosene.
Okay, systematic. Now, what about compounds with, say, two fused rings? Bicyclic compounds.
Ah, yes, bicyclic compounds. They follow similar principles, but have their own special naming rules. You identify the two bridgeheads, the carbons where the rings fuse.
Because you get extra points.
Exactly. Then you count the carbons along the three paths connecting those bridgeheads. This gives you a unique bracketed numbering system, like XYZ, that tells you the exact shape.
Sounds a bit intricate.
The numbering can be, yes.
Huh.
You start at a bridgehead, number along the longest path first, then the second longest, then the shortest, always ensuring substituents get the lowest possible numbers.
So it's still about creating that precise chemical address.
Absolutely. This kind of detailed naming is essential for understanding complex natural products, like the hydrocarbon core of certain vitamin D analogs.
And this detailed nomenclature isn't just for textbooks, right? It's fundamental to how we understand the drugs we take every day.
Definitely.
Pharmaceuticals often have incredibly long, cumbersome IUPAC names. That's why we have shorter, more user-friendly names.
Like the trade name, think Nexium.
Right, or Lipitor, and the generic name.
Like isometorbazole or atorvastatin, yes.
If you look at common drugs like aspirin or ibuprofen, their simple, familiar names stand in stark contrast to their often very complex IUPAC names.
It really highlights the practical need for different naming conventions, balancing that chemical precision with everyday usability.
Okay, let's shift gears a bit from naming to another fundamental concept, isomers. Specifically, constitutional isomers.
Right, compounds with the exact same molecular formula, but a different connectivity of atoms, same parts, assembled differently.
And what's truly astonishing is how the number of possible constitutional isomers just explodes as you add more carbons.
It's incredible. For example, C6H14, just 6 carbons and 14 hydrogens, has 5 constitutional isomers.
Manageable.
Okay. But jump to 30 carbons, C30H62, you're looking at over 4 billion possible isomers.
4 billion. That's mind-boggling. Does that mean, like, in nature you'd find all 4 billion, or some just theoretical?
That's a great question. While theoretically possible, no, not all are equally stable or even exist for long periods. Nature, much like our car engines actually, often prefers the most stable, the most relaxed configurations.
Ah, okay.
In fact, a crucial problem-solving technique when you're trying to draw these isomers is to use IUPAC naming to check for duplicates.
Use the name to check.
Exactly.
Huh.
If two different drawings yield the same IUPAC name, then they are in fact the same compound, just drawn differently.
Right.
Saves you from counting the same molecule twice.
This concept is really important when we talk about things like octane ratings in gasoline, isn't it?
Absolutely. Gasoline is a complex mix, and the octane rating reflects how well it performs in an engine. Straight-chain unbranched alkanes cause engine knocking.
That pinging sound.
Right. But branched alkanes, like the various isomers of heptane or octane, have higher octane ratings. They burn more smoothly because they're more stable.
More stable. So how do we actually compare the stability of these different isomers? How do we measure it?
We use a concept called heat of combustion. This is the heat released when an alkene reacts completely with oxygen to produce carbon dioxide and water.
Burning it.
Essentially, yes. The less heat released, the lower the initial energy of the compound, meaning it was more stable to begin with.
Okay, so lower heat of combustion equals more stable.
Correct.
So the key insight here, a truly fundamental concept in organic chemistry, is that branched alkanes are generally lower in energy and therefore more stable than their straight-chain counterpart.
That's a major takeaway. And it explains why refineries want those branched hydrocarbons in our gasoline.
Speaking of gasoline, where do we actually get all these alkanes from?
Primarily from petroleum, which literally means rock oil. It's a remarkably complex mixture of hundreds of hydrocarbons, mostly alkanes and cycloalkanes, formed over millions of years from decaying ancient organisms.
A fossil fuel.
Exactly. Once extracted, the crude oil goes through a refining process, mostly distillation.
Separating it out.
Right. It separates the oil into different fractions based on their boiling points. You get natural gas, various solvents, gasoline, kerosene, heating oil, lubricating oils, waxes, and finally asphalt.
But you said gasoline demand is high.
It is. The challenge is that crude oil only yields about 19% gasoline directly through distillation, which isn't nearly enough.
So what do they do?
Two main industrial processes are used to boost that yield. First, cracking, which uses heat and catalysts to break larger alkanes into smaller ones suitable for gasoline.
Breaking them down.
And second, reforming, which uses catalysts to convert those less desirable straight-chain alkanes into more valuable branched hydrocarbons and also aromatic compounds.
Why is reforming so important? Just for yield?
Yield, yes, but also quality. Those branched hydrocarbons and aromatics significantly reduce engine knocking, leading to smoother performance and higher octane ratings. So the gasoline you buy is actually a sophisticated blend, carefully tailored even for different climates and seasons.
Wow. It's more complex than just pumping liquid. But this brings us to a bigger, sort of unavoidable question. Petroleum is non-renewable.
Indeed. What innovations will replace it as our primary energy source and the source of organic compounds for plastics, pharmaceuticals, and so much more? That's a huge challenge facing chemists and engineers today.
Absolutely. Okay, before we move fully into conformations, you mentioned physical state.
Right. The physical state of alkanes, gas, liquid, solid changes with their molecular weight. This is due to intermolecular forces, specifically London dispersion forces.
Weaker forces for smaller molecules.
Exactly. Low molecular weight alkanes like methane and ethane are gases at room temperature. Mid-range ones like hexane and octane are liquids, and very high molecular weight alkanes are waxy solids.
Which leads us naturally to polymers.
Like polyethylene, yeah.
Yeah.
Polymers are giant molecules formed by joining together many small repeating units called monomers. In polyethylene, the monomer is ethylene.
And polyethylene is everywhere.
Absolutely ubiquitous, from plastic bottles and garbage containers to, believe it or not, bulletproof vests. Billions and billions of pounds are produced worldwide every year.
Okay, so now let's really get to the heart of it. Molecular flexibility, conformational analysis.
Right. Remember, rotation around those carbon-carbon single bonds allows molecules to adopt various three-dimensional shapes, or conformations.
The dance moves.
Dance moves. Some are high in energy, some are low. To visualize these subtle twists and turns, we use a special drawing tool called the Newman projection.
How does that work?
It allows us to look directly down a specific carbon-carbon bond. You represent the front carbon as a dot and the back carbon as a circle. The grooves attached are shown radiating from the dot or the circle.
Looking straight down the bond axis.
Okay. In a Newman projection, the angle between a group on the front carbon and a group on the back carbon is called the dihedral angle, or sometimes torsional angle.
Dihedral angle.
As that CC bond rotates, this angle changes, giving us, theoretically, an infinite number of conformations. But two specific types are really key.
Which are?
The staggered conformation, where the groups on the front and back carbons are maximally separated, think 60 degrees apart. This is the lowest energy conformation.
Most stable.
And the eclipse conformation, where the groups are aligned, one directly behind the other, dihedral angle of 0 degrees, this is the highest energy conformation.
Least stable. Why the energy difference?
The energy difference between the lowest energy staggered and the highest energy eclipse conformation is called torsional strain. It represents the energy cost of forcing those groups past each other.
A barrier to rotation.
Exactly. Quantum mechanical calculations show it's related to electronic interactions. In the staggered conformation, there's a favorable interaction between electron clouds that gets disrupted when the molecule rotates into an eclipsed conformation, increasing its energy.
Okay, so electrons bumping into each other, basically.
It's a bit more subtle, involving molecular orbitals, but yes, increased electron repulsion is a major factor in the eclipsed form. For ethane, with 3 pairs of eclipsing hydrogens, each HH eclipsing interaction costs about 4 kilojoules per mole.
4 kilojmol for HH eclipsing. What about propane? It has a methyl group.
Right. Propane's torsional strain is slightly higher, about 14 kilojmol total. Since we know each eclipsing costs 4, and there are 2 of those.
Then the interaction between an H and the methyl group must cost more.
Precisely. An H eclipsing a methyl group costs about 6 kilojmol.
Okay.
What's key isn't necessarily memorizing every single number, but understanding the concept. Even small groups repel each other if forced too close. These tiny repulsions, these steric interactions, add up and drive a molecule to spend most of its time in its most stable, lowest energy shape.
Butane gets even more complex, right? Because it has 2 methyl groups.
Exactly. It's staggered, and eclipse conformations aren't all equal in energy anymore. Let's look at the staggered conformations first. The lowest energy one is the anti-conformation, where the 2 methyl groups are as far apart as possible, 180 degrees dihedral angle.
Anti. Makes sense.
But there are 2 other staggered forms, where the methyl groups are only 60 degrees apart. These are called gauche conformations.
Gauche?
Yes, gauche. They are slightly higher in energy than the anti-conformation, by about 3.8 kilojmol. This energy difference is due to gauche interactions.
Which is the type of...
Steric interaction. Essentially, the electron clouds of those 2 relatively bulky methyl groups are bumping into each other slightly, even though they're technically staggered. It's steric strain due to proximity.
Okay, so anti is best, gauche is slightly worse. What about the eclipsed forms of butane?
Those vary too. The highest energy eclipse conformation is the one where the 2 large methyl groups eclipse each other directly. That costs a lot of energy, about 11 kilojmol, just for that CH3-CH3 interaction, leading to a total strain of 19 kilojmol for that conformation.
Ouch. Big groups eclipsing is bad.
Very bad, energetically speaking. The other eclipse conformations, where a methyl eclipses a hydrogen, 6 kilojmol, and hydrogens eclipse each other, 4 kilojmol, are lower in energy than the methyl eclipse, but still much higher than any staggered conformation. Total strain there is about 16 kilojmol.
So, understanding these different energy costs, torsional strain from eclipsing, steric strain from gauche interactions, allows us to predict the relative stability of various conformations and which shapes the molecule prefers.
Exactly, and that ability to predict preferred shapes is critical.
Which brings us back full circle to drug design.
Precisely. The concept of a pharmacophore, the specific 3D arrangement of atoms or functional groups required for a drug to bind effectively to its biological target like an enzyme or receptor, is absolutely central.
Okay.
Think about it. A rigid molecule like morphine has its pharmacophore essentially locked in place. It fits its receptor or it doesn't.
Right. Less wiggle room.
But a flexible molecule like methadone, which also treats pain but has a very different structure with many single bonds, can adopt multiple conformations. Only some of those conformations will actually have the correct 3D shape, the correct pharmacophore, to bind to the receptor.
So flexibility can be good, but maybe only one pose works.
Often, yes. But the groundbreaking application we mentioned earlier is with new anti-HIV drugs, like rilpivirine, approved back in 2011.
The flexible one.
Yes. Its flexibility, enabled by rotation around 5 key single bonds, allows it to change its shape slightly. This means it can still bind effectively to the viral enzyme it targets, even when the virus mutates and changes the enzyme's geometry slightly.
It adapts.
It adapts.
Yeah.
This makes it significantly harder for the virus to develop drug resistance. It's a revolutionary way of thinking, leveraging conformational flexibility to combat mutation.
That's fascinating, using basic chemical principles, bond rotation, to solve such a complex medical problem.
It really shows how fundamental understanding can lead to life-changing applications.
Okay, let's switch from chains to rings. Cycloalkanes and their conformations. You mentioned Bayer's strain theory earlier.
Right, late 19th century. Bayer assumed rings were planar, like flat polygons. Based on ideal geometry, he predicted smaller rings, like cyclopropane and cyclobutane, and also larger rings, would be strained because their bond angles deviate from the ideal tetrahedral angle of 109.5 degrees. He thought cyclopentane, with angles close to 108 degrees, would be the most stable.
But he was wrong.
Well, partly right about strain in small rings, but wrong about clinarity and overall stability. Experimental evidence, specifically measuring heats of combustion per CH2 group, quickly showed a different picture.
What did the experiments show?
They showed that cyclohexane, the six-membered ring, is actually the most stable, essentially strain-free. Cyclopentane has some strain, and cyclopropane and cyclobutane are highly strained. Crucially, larger rings weren't necessarily more strained than cyclohexane.
So the key takeaway.
Rings are not planar. They pucker and twist into three-dimensional conformations to minimize their total energy, which is a combination of angle strain and torsional strain.
Let's look at specific rings then. Cyclopropane.
Cyclopropane, the three-membered ring, is highly strained. It suffers from severe angle strain. The CCC bond angles are forced to be 60 degrees, way off the ideal 109.5. The bonds are literally bent.
Dead bonds.
Plus, it has significant torsional strain because it is planar, meaning all its hydrogens are locked in an eclipsed conformation. High angle strain plus high torsional strain, very unstable and reactive.
Reactive means it wants to break open.
Exactly. It undergoes ring opening reactions readily. But this instability had a surprising application.
The anesthetic.
Yes. Cyclopropane was actually used as an inhalation anesthetic starting in the 1930s. It worked quickly and had few side effects like vomiting. But its extreme instability due to that ring strain made it incredibly flammable and explosive. Even a tiny static spark in the operating room could cause a detonation. Yeah. That inherent danger led to its replacement by safer anesthetics by the 1960s. It's a powerful example of how molecular structure directly impacts practical and sometimes dangerous applications.
Okay, so cyclopropane is strained. What about cyclobutane and cyclopentane?
Cyclobutane, the four-membered ring, has less angle strain than cyclopropane. 90-degree angles are close to 109.5 than 60. But it still experiences significant torsional strain if it were planar. So it puckers slightly out of plane to reduce that eclipsing.
It bends a bit.
Right. Cyclopentane, the five-membered ring, has even less angle strain, and it puckers quite effectively into an envelope or half-chair shape to minimize torsional strain. It's much more stable than the smaller rings, but still not quite as stable as
Cyclohexane, the champion.
the strain-free champion.
Right.
Cyclohexane achieves this stability primarily through its famous chair conformation.
The chair, why is it so stable?
Two main reasons. First, all the CCCC bond angles in the chair are very close to the ideal tetrahedral angle of 109.5 degrees, so there's virtually no angle strain. Second, if you look down any CC bond using a Newman projection, all the hydrogens are perfectly staggered.
No torsional strain either.
Exactly. Minimal angle strain, minimal torsional strain. That's the recipe for stability.
You mentioned a boat conformation, too.
Yes, cyclohexane can also exist in a higher energy boat conformation. While it avoids angle strain, it suffers from significant torsional strain because hydrogens on 4 of the carbons are eclipsed.
Like looking down the sides of the boat.
Right. Plus, there's steric strain between the two hydrogens pointing inwards at the top of the boat. We call these flagpole interactions.
Flagpole hydrogens bumping into each other.
Precisely. The boat can twist slightly into a twist boat conformation to relieve some of this strain, but it's still much higher in energy than the chair. So at room temperature, almost all cyclohexane molecules are in the comfortable chair conformation.
And drawing these chairs correctly is important, right?
Absolutely crucial. It's a fundamental skill. You learn to draw the basic skeleton, start with a wide V, draw 2 parallel lines slanted down, then connect them with 2 more parallel lines slanted up. Takes practice, but it's essential.
Once you have the skeleton.
Then you add the hydrogens, or other substituents. Each carbon on the chair has 2 positions available. One is axial. These bonds point straight up or straight down, alternating around the ring.
Vertical.
And the other is equatorial. These bonds point out from the equator of the ring, roughly parallel to ring bonds 2 carbons away. Getting all 12 positions, 6 axial, 6 equatorial, drawn correctly is key.
Okay, now let's put something on the ring. A monosubstituted cyclohexane. 1 branch.
Right. So you have a cyclohexane ring with, say, a methyl group attached. That methyl group can be in either an axial position or an equatorial position.
Axial or equatorial, are they equally stable?
No, they're not. These two forms are rapidly interconverting at room temperature through a process called a ring flip.
It flips over.
Not literally flipping like a pancake. It's a complex conformational change where all the CC bonds rotate, causing the chair to convert into the other chair conformation.
Yeah.
What was axial becomes equatorial, and what was equatorial becomes axial.
Ah, they swap positions.
They swap roles, yes. And the crucial rule here is stability. The conformation where the substituent is in the equatorial position is generally preferred. It's lower in energy.
Why is equatorial better?
Because when a substituent, especially one larger than hydrogen, is in an axial position, it experiences unfavorable steric interactions with the other two axial hydrogens on the same side of the ring, 3 carbons away. We call these 1003 diaxial interactions.
Steric clash.
Exactly. They're essentially gauche interactions, similar to what we saw in butane. Putting the substituent in the roomier equatorial position avoids these clashes.
And the bigger the group, the bigger the clash, so the stronger the preference for equatorial.
Precisely. A small group like fluorine has only a slight preference, while a large group like tert-butyl has an overwhelming preference for the equatorial position. We can even quantify these energy differences. A methyl group costs about 7.6 kilojmol to be axial.
So the molecule will spend most of its time with the methyl group equatorial.
Overwhelmingly so. Though chemistry always has interesting twists.
Exceptions.
Sometimes. In specific molecules, like derivatives of myoinositol or certain dioxins, sometimes smaller groups like OH might actually show a slight preference for the axial position due to other subtle electronic or hydrogen bonding effects. It reminds us that while steric bulk is often dominant, it's not the only factor.
Always more complexity beneath the surface. Okay, what about dissubstituted cyclohexanes? 2 groups.
Now we add another layer. Besides axial and equatorial, we need to consider the 3-dimensional orientation of the substituents relative to the plane of the ring. Are they pointing up or down?
Up or down, how do we show that?
Often with wedges, UP, or dashes in flat drawings. But here's the absolutely critical point. This UP-Dayton configuration for each substituent does not change during a ring flip.
So if a group starts UP, it stays UP after the flip.
Yes, it might switch from axial to equatorial or vice versa, but its UP-Dayton orientation relative to the ring is fixed. It's part of its inherent structure.
Okay, that's important. So when comparing the stability of the 2 chair conformations for a dissubstituted ring.
First, you draw both chairs, making sure to keep the UP-Dayton configuration correct for each group as it switches between axial and equatorial. Then you compare stability. The conformation with more substituents, especially larger ones, in the equatorial position will generally be more stable.
What if it's a trade-off, like one group is axial, one equatorial in both chairs?
Good question. Then you need to look up the energy cost, the 1 for 3 diaxial interaction energy, for each group being axial. The conformation where the smaller axial interaction energy cost is paid is the more stable one. Basically, you put the bigger group equatorial if possible.
Makes sense. Minimize the biggest steric clash. This leads to cis-trans isomerism, right?
Exactly. In cycloalkanes, cis means the 2 substituents are on the same side of the ring, both UP or both down. Trans means they are on opposite sides, one UP, one down, down, and.
And we often use those flattened drawings, Haworth projections, to show this.
Yes, Haworth projections are useful for clearly visualizing cis-trans relationships. But the vital distinction is that cis and trans isomers are stereoisomers. They are fundamentally different compounds with different structures and different physical properties.
And crucially,
they cannot be interconverted by ring flips. A ring flip only changes axial equatorial positions, not the inherent cis or trans relationship, the UP-DON configuration. For example, trans 1,2-dimethyl cyclohexane is more stable than its cis isomer because the trans isomer can adopt a chair conformation where both methyl groups are equatorial. The cis isomer is forced to have one axial and one equatorial in any chair conformation.
Different compounds, different stabilities. Got it. What about even more complex systems?
We can have polycyclic systems. A common example is Decalin, which is essentially 2 cyclohexane rings fused together.
2 chairs joined.
Exactly. And just like with dissubstituted cyclohexanes, you can have cis-Decalin and trans-Decalin, which are stereoisomers based on how the rings are fused. Many important natural compounds like steroids, cholesterol, testosterone incorporate these fused ring systems, often based on Decalin structures. Their shapes are critical to their biological function.
And other polycyclic examples.
Another common one is norbornane. You can think of it as a 6-membered ring that's been forced into a boat conformation and then locked in place by a 1-carbon bridge across the top.
A bridged boat.
Right. It's found in various natural products like camphor, which gives Vicks VapoRub its smell, and camphene.
Okay, and the grand finale you mentioned earlier.
Ah, yes. Let's connect this all back to the structure of diamond. Diamond is essentially a giant, three-dimensional network polymer of carbon atoms.
How does it relate to cyclohexane chairs?
The structure of diamond is based on countless fused, six-membered rings, all locked rigidly into perfect chair conformations. Every single carbon atom is bonded tetrahedrally to four other carbon atoms, extending outwards in all directions.
A massive lattice of chairs.
A massive, incredibly strong lattice of chairs. Its extreme hardness and stability come from the fact that scratching or breaking a diamond requires breaking billions and billions of these strong carbon single bonds within that perfectly ordered, strain-free structure. It's a beautiful illustration of how understanding the stable conformation of a simple six-membered ring helps explain the properties of one of the hardest materials known.
Wow. And there you have it, our deep dive into alkanes and the cycloalkanes. We've really covered some ground from understanding how to name these fundamental building blocks,
Getting that nomenclature down.
to dissecting the intricate dance of their conformations, the chairs, boats, twists, and flips. We've seen where these compounds come from petroleum, how they're processed,
Cracking and reforming.
how their shapes dictate everything from the fuels that power our cars to the plastics that shape our daily lives.
And even how their subtle movements, that flexibility, are being harnessed in the design of life-saving drugs and give structure to materials like diamond. It truly highlights the elegance and the utility of understanding molecular shape and flexibility in organic chemistry. These seemingly simple concepts really unlock immense understanding about the world around us.
So the next time you pick up a plastic bottle or fill your car's tank or even admire a diamond, maybe you'll think about that invisible world of molecular shapes and the subtle dance of conformations that dictates their very existence and properties.
It's happening all around us all the time.
This understanding isn't just for chemists, it's really about how we grasp the mechanics of our physical world. Thank you for being part of our deep dive family. Keep diving deep.